In this video we're going to cover the concept of acceleration. So I'd like you to imagine that we have a ball here on top of the ramp and it's going to be rolling down. As it rolls down, it's speeding up. And if we were to graph that on a position graph, it would look like this. So x for position, t for time, and the graph would look something like this. The reason I know it's curved is because the slope on the position graph represents the velocity. So the slope is getting steeper and steeper and steeper. And so on a velocity graph, v versus t, it would look, if I were to graph these slopes with respect to time, I would get a graph that looks like this. And so you'll notice that the velocity is increasing with time. And the rate at which the velocity increases with time, we have a name for this. We call this acceleration. So to define acceleration, we call it the rate. It's defined as the rate at which velocity changes. And there are several ways you can tell if something is accelerating. Number one, if the motion of an object is speeding up, or if the object is slowing down, or if the object is changing direction. In each of these cases, we would say that the object is accelerating. We also have an equation to calculate acceleration. And the equation is acceleration is equal to the final velocity minus the initial velocity divided by the time. So let's take a moment to look at what is called a motion map. And these are also known as dot diagrams. And they're a way for us to represent an object's motion using dots and arrows. So I'd like you to imagine with me that we have a car here. And this car is moving to the right. And this car is speeding up. This car unfortunately has an oil leak. So as it's moving, it's going to drip oil, and it's speeding up to the right. And so if you were to look at the oil drips, they would be getting farther and farther and farther apart. Now if you saw these dots, you wouldn't know if it's moving to the right or left. So I'm going to add some arrows. So the arrows tell you the direction it's moving, the distance between the dots, how they're getting farther and farther apart, tell you that it's speeding up. So this car is moving to the right, and it's speeding up. I'm going to write that, speeding up. And the acceleration is also to the right. So acceleration has a direction. And when the acceleration is in the same direction as your velocity, then the object will be speeding up. Now let's take a look at another situation here. Let's say that the object was slowing down. So the dots would be getting closer and closer together. Here we have also the arrows to indicate the direction of the car. Okay, so the dots are getting closer and closer together, so that lets us know that this object is slowing down. Okay. These are the velocity vectors, and the acceleration is going to be towards the left. So when an object is slowing down, the velocity and the acceleration will be in opposite directions. Now what if the car was moving at constant speed? Let's say the car was constant speed moving to the right. Then the dots, the oil drips, would be equally spaced. So when the dots are equally spaced, that tells you that the object is moving at constant velocity. You could say constant speed if it's in the same direction we would say constant velocity, which means that it's moving at a constant speed and moving in the same direction. So now let's take a look at a couple examples using the equations to solve for acceleration. So here we have a car. It's moving to the right. And at time equals 0, it has a velocity of 30 meters per second. And I'm going to draw an arrow to represent the velocity. So we're going to call this the initial. This is the initial velocity. And then at 3 seconds, the car has a final velocity of 12 meters per second. So this car is moving to the right, starts with 3 meters per second, and now it's 12, so it's going faster. I'm going to draw a longer arrow to represent that faster velocity. So now I'm going to use my acceleration equation, which is acceleration is equal to final velocity minus initial velocity divided by the time. The final is 12, initial is 3, divided by the time is 3 seconds. So 12 minus 3 is 9, divided by 3, and I get 3 meters per second squared. And this acceleration is positive. We're making right positive, and so I'm going to also write right. Okay, so acceleration is a vector, so it has a magnitude and a direction. So I want to take a moment to think about what this 3 meters per second squared means. So we can also rewrite this as 3 meters per second per second. What does that mean? What this is telling us is that the velocity changes by 3 meters per second every second. So that's where that second and second is, because there's an S right there and there's another second right there. So 3 meters per second means every second the velocity is changing by 3 meters per second. Okay. Let's take a look at another problem. And this time the car at the start has a velocity of 26 meters per second, and that's the initial. I'm going to draw an arrow for the initial velocity. And the final velocity is going to be at time equals 2 seconds, and the final velocity is 10 meters per second. So this time the velocity is decreasing, so I'm going to draw a smaller arrow, VF. And once again, I'm calculating for the acceleration. So the acceleration is final velocity minus initial velocity divided by t. So we have final is 10, initial is 26, the time is 2, so I have negative 16 divided by 2, which is negative 8 meters per second squared, and this is going to be to the left because we got a negative acceleration, and I'm going to assume right is positive. We'll assume right is positive here, and so negative just means the acceleration is towards the left.